It's like, okay. Well, thank you, and thank you again for the. It's a pleasure to be here and for the invitation. I thought to give a little bit of background about what my role is and what I'm going to be talking about. So this is not going to be anything about genomics data or biological data. This is about air pollution research and population health. My background, I'm a biostatistician, a professor of biostatistics, and so I'm going to be telling you how during my career, I've been trying to link heterogeneous sources of data. These are data that already exist, so there is no primary data collection. These are existing data that have been collected by the government, and then my role has been linking these databases and developing statistical methodology to analyze these data, and hopefully I was able to address some interesting research question. I'm also playing a role, an administrative role at Harvard in trying to understand and consolidate high performance computing across the different schools at Harvard University, as we just being on the same, along the same type of discussion that been before, in terms that increasingly our faculty and PI needs to have a better availability and better access to high performance research computing as well as data storage. So that is the brief introduction, and let me go through, let's see, how I move. Okay, this is not a good start. Sorry.
You're not a Mac user, are you?
I do, I'm a Mac. Oh, I just need to move a slide, that's all.
Okay, so you can go there.
Perfect, that's all I need to do.
And then you can point with this.
Okay, I don't even need to point. So these are the three types of scientific investigation I've been involved on: health effects of air pollution, and more recently, how we estimate mortality risk associated with heat waves in the context of climate change. So I was a little bit intimidated by the other talks, although I wasn't surprised that when I talk in population health about large data, I feel like I'm a little bit, small in contrast to other type of genomics data. But in my world, this is a big data. And so just to give you an example and a very simplistic type of representation of the things I am dealing with. So what I've been trying to do, I've been trying to go after existing data that the EPA has collected on ambient level of air pollution for different pollutants, that NOAA has collected in terms of weather variables, that the census has collected in terms of socioeconomic status, and both the National Center of Health Statistics as well as claims data from Medicare. Understanding all of these existing databases, how they're collected, at which spatial and temporal resolution have been collected, and then try to integrate them, link them in different ways to then address questions related to health effects of air pollution and climate changes on a national scale, and then advising the government back, specifically APA, about the adequacy of the current level of air pollution. So just to give you some, I'm not expecting, and I put this together specifically because I was asked to provide some detail about the data. I'm not expecting you to read all of that table, but I just want to give you a sense that all of these different data sources, again, because we don't do any primary data collection, they are collected at different level of spatial and temporal resolution. And that's actually why for a biostatistician and throughout my career has been a little bit of a wonderful opportunity. It's like for a kid walking into a candy shop, because there are all kinds of statistical challenges, and everything I know about biostatistics, I know because I have to face some concrete challenges in the linkage of these data. So for example, I mean, we all know that the census data is available every 10 years at different level of spatial resolution. The weather data, there are several thousands of monitoring stations around the country. They actually measure very reliable weather data and at the hourly level. Air pollution monitoring network, there are several different monitoring networks. They are all maintained by the Environmental Protection Agency. There are several thousands monitoring stations in the US that measure ambient level of particulate matter, ozone, and many other primary pollutants. They measure these data different sampling scheme. Some pollutants are measured daily. Some other pollutants are measured one every 3 days. And so there are all kinds of different challenges in terms of understanding every single data in particular and then linking them. I also should mention that, well, census data is available and free. Air pollution data is available and free. Weather data you have to buy, but it's really, really inexpensive. I mean, it's really, you can buy out of your pocket. Now, for health data, it gets a little bit more complicated. So in this specific talk, I'm going to talk about, I'm going to focus in terms of claims data, and the claims data coming from Medicare, and in particular, Medicare Part A. Medicare Part A are hospitalization records. Now, this is an extremely rich source of data that is not publicly available. You have to buy the tapes, and it's available. It's available with a couple of years lag. So right now we're in the process. We have already been able to buy and acquire and link the Medicare data for 2010. But it's very rich data in terms of that potentially you can buy year after year, individually link a subject over time. And it's 100%. So we will be able to acquire the entire Medicare billing claims for everybody in the United States enrolled in the Medicare, so which is approximately 90% of the population in the US over 65 years old. These records can be individually linked, so we do have the availability to follow a trajectory of a person enrolled in Medicare over time, understanding the tracking every single hospitalization that this person had by ICD-9 code. And we also know, specifically to address question environmental health, the place of residence up to a zip code. So there are these, we have the developing algorithm to link the place of residence of that person up to a zip code to the closest air pollution monitoring network to make inference about how that person enrolled in the Medicare, what's the level of air pollution or weather that the person has been exposed to. Now, Part A is only collect data regarding hospitalization. There are Medicare, as also Medicare Part B. They are doctor visit and outpatient. We have not been able yet to acquire the 100% data and link that data. That's also, you can imagine the level of complexity and dimensionality of the data explode, because if you think about how many hospitalization you have, hopefully much lower number than doctor visit. And so the hospitalization data, although very rich, is clearly simpler than the Part B, which is the doctor visit. There is also Part D, which is medication use, which is also available. Now, also, let me make a comment here. One of the, I think, greatest success of collaboration between government agency has been the linkage of SEER, which is the tumor registry data, with Medicare. This is existing link databases, and if you search the literature, there have been a really tremendous amount of advancement in cancer research in terms of population health, because the government agency have been come together and they have linked the SEER with Medicare. This is not what I'm doing here. I'm linking air pollution data to claims data. So I don't have, this is not a big consortium. There is not big grant money. This is really me and other 3-4 folks in my lab in creating what we call a data center, where we are taking all of this data and our expertise and try to link together, but embedded within development of statistical methodology, because you can only do that, I think, if you really understand what are the challenges in trying to integrate heterogeneous source of data. So there are all kinds of challenges that we have been trying to sort it out. I think with size, I mean, now we are like on a 10 terabytes of data, and within a decent investment, we can deal with this, but clearly this is expanding, and so we can host the data center in a closet. Medicare data is secure data, so it cannot be shared on the network. So we need to define better way to access the network, and all other things that I think many of you have been already talking about. So I want to give you an example of what type of scientific question we will be able to address by linking data that already exist. So we have created, by the use of Medicare data, what we call the National Medicare Cohort Study. So these are like now 10 years, and as Medicare data become available, we buy the additional tape. So this is something that we are committed to continue to update prospectively. So as I said, these include billing claims. We have the date of service, we have the disease, we have age, gender, and race, we have the place of residence, and then basically what we do, we are linking it to, in this particular study, we are linking it by counties to the National Pollution Monitoring Network. And so what this map shows is just one of the examples of the study that was being conducted, where basically we take 204 counties in the United States that are heavily monitored in terms of ambient level of air pollution. And then we were looking at the association between day-to-day changes in ambient level of different pollutants in the air and day-to-day changes in hospitalization rates for different diseases. So this is an example of the time series data that we can construct as a result of accessing Medicare data. These are daily hospitalization rates for heart failure, for stroke, for COPD, and daily ambient level of PM 2.5 for the county of Los Angeles. So as a result of this integration of developing, of gathering data sources and linking it, we have been providing national evidence about the ambient level of particulate matter on hospital admission for cardiovascular diseases. And also I think that the reason why I put these two figures one next to each other, because thanks to the integration of these databases, we were able to advance one of the fundamental questions, which was as whether finer particulate matter, so PM 2.5, are more harmful than coarse particulate matter, which has a PM of a size between 2.5 and 10. Again, the national ambient, the ambient quality system from the EPA gave us availability of downloading both PM 2.5 data and cohorts data. You can imagine the ambient level, the health effects of pollution are really, really small. And so you need millions in order to be able to detect the effects. And so what we have on the panel on the left are the national average estimates of the ambient level of fine particulate matters, and what we have in the right are the national estimates of the ambient effect of coarse PM. And so from the plot on your right side, you can see there is no effect of coarse PM, where there is a strong effect of fine particulate matter on cardiovascular disease, but only on the east part of the United States. Now, why I'm mentioning the difference between fine particulate matter and coarse particulate matter? Because right now, in the state of science in our pollution epidemiology, it's pretty well known that ambient exposure to fine particulate matter has adverse health effect, cardiovascular, neurological, and mortality. The next big question is, which is the chemical component of particulate matter and which is the emission sources that is more harmful to health. Now, this is a really, really tough question to address. And again, you need a lot of data to be able to address this question. EPA has been let me actually go to this for a moment. This is actually where I'm jumping. The EPA has been investing a tremendous amount of resources to also develop another type of air pollution monitoring network, which is called the Speciation Trend Network, that doesn't only measure fine particulate matter in total mass, but measure for several hundred locations in the United States the different chemical components of particulate matter. So this map shows, for example, the average level of elemental carbon, of silicon and sulfate as the different chemical components of PM 2.5. So again, this data is free, is publicly available, and because we will be able to gather Medicare data, which is available at the national level, we were able to link air pollution data on chemical component of PM 2.5 to Medicare data and then start addressing questions about health effects of chemical components of PM2.5 data. Now, similar thing we have done with the effect of ambient level of ozone on mortality. This is basically national average estimate of the percentage increase in mortality associated with a 10 microgram in cubic increase in the daily level of ozone. And so what we have is that on the same day, if you have the ozone increase of 10 units, you have a 0.2% increase in mortality. Again, these are small effects. This is not the effect of smoking, but this is the effect of breathing ambient level of ozone. And so you can imagine that smaller is the effect, but everybody is affected because you can choose whether or not you smoke a cigarette, but you cannot choose whether or not you smoke ozone. And so the population attributable risks are pretty large. So these are just examples. This is actually, I want to show you, this is a really very, very recent example that what we have done actually was a try by the integration of these data sources, it was to try to address specifically a regulatory policy question, which was the following. So the EPA has been investing billions of dollars in cleaning air, and it's very well known that the ambient level of PM2.5 have been declining very sharply in the last 20 years. Although in the last 10 years, past the year 2000, the changes in PM2.5, although PM2.5 is continuing to decline, have been changing at a much slower rate than before. I mean, basically what people argue is most of the cleanup has already been done. Do we need to continue to clean up the air? So what we have done, we have linked the more recent changes in PM2.5 after the year 2000 to 2007 to life expectancy data for the largest 545 counties. And this is a map of the counties included in the studies. And so what we have found is that even with the smaller changes in PM2.5 and more recent changes in PM2.5, we continue to improve life expectancy. So the other important topic, and I think a very controversial one, is climate change and health and the public health impact of climate change. And that is extremely controversial, extremely difficult topics. But again, this is another opportunity, I think, for us because data exists, is available, and we can access to, and we can make significant advances. This is I just cut and paste. I'm sure many of you seen the front page of the New York Times yesterday. I think it's pretty well known that I would say, in my own opinion, climate change is happening, and in 2012 it was the hottest year in the US. So again, what we have done in the context of climate change, well, this is really in the context of heat waves and mortality. Again, remember, your first slides, I told you that we can download, well, you can buy tapes from NOAA to get daily level, actually hourly level of weather for several thousand monitoring stations in the United States. Again, we have linked that to the administrative data and develop statistical methodology to estimate city-specific relative risk of mortality associated with heat waves for the largest 105 counties in the United States. It's interesting to see, and I know we don't have the time here to go into all the details, I have ranked the counties by the large geographical region in the United States. You can see that the Northeast, the second panel, is one which is really highly affected. Again, and that has to do with the notion of adaptation, which is something that we are exploring now. You can imagine that in a city like Boston, if you have an heat waves, the city of Boston is not prepared as another city. So so there are two concepts. One is the relative increase of temperature with respect to what you're used to, but also the length and the intensity of an heat wave. So a more intense and more long heat waves in a city that is generally of a cooler climate could have a much harmful effect of a city of a warmer climate. So I want to conclude really with the idea of data integration in the context now moving in the context of climate change. So there is now a tremendous amount of effort in the climate change community in predicting weather for the future and making different assumptions about different emission scenarios, how the weather is going to change how the air pollution is going to change. And so now we can start making prediction about how the impact on health is going to happen and how we're going to account for the fact that we, as a population, we will be adapting over time. I want to show you a case study, a simple example of something that we have done only for one city in Chicago. So what we have done for the city of Chicago, we have took historical data, the data I show you, for the last 20 years. So we have daily weather, we have pollution, we have mortality, we have claims data. And so the first box on your top left show basically our approach of linking heterogeneous data and then estimating the present day effect on mortality associated with a heat wave. So from the first box, I was able to estimate if I have a heat wave in Chicago of these many days, of this intensity, what is going to be the effect on mortality. Now, on the bottom, we have been established a collaboration with people at NCAR, which, by the way, again, this data is publicly available. What they do, they have this global climate change model. They have a different hypothesis about emission scenario. They have a different modeling. Many of them I don't understand. They predict weather for the future, and then do a downscaling to understand what's going to happen on a local scale. Well, we put the two things together, and we will be able to predict the future number of heat waves. And then on the last block, you have to make assumption about what's going to be the future condition of the population, and so to come up with a future heat wave excessive mortality. Now, we have done the calculation, we have published a paper, but the reason why I'm doing this is a proof of concept in terms that ideally, with enough endurance, you can get prediction of climate change out of the web, of course, with people understand the data, with weather data, with statisticians, with health data, and try to make exercise about what's going to be the future impact on health associated with climate change. So I give you an example. So these pictures show what we have found for the city of Chicago. These are the different emission scenario. And on the top right, we have predicted that, of course, there were all kinds of assumptions and sensitivity analysis and so on. But basically, we are predicting what's going to be the excess number of deaths associated with every additional heat wave that have been predicted based on this climate change model. So I'm going to just conclude to the fact that in the context, in the bigger question about how climate change will impact environmental stressor and impact human health, I think that although a really challenging exercise, is something that I don't think that the size of the data is something that it's impossible to deal. I mean, I think this is large data, but clearly accessing to the cloud is something that can be overcome. I think that these data are available. So there is, I mean, to some degree, I mean, again, the cost of data, it's not a big obstacle. I mean, again, they are not free, but they are not, giantly expensive. It's really human. It's really people that wanted to understand the data and have the endurance of linking them and have the knowledge and the expertise of understanding all the different challenges. So I think I'm going to skip this slide and just say that I think, of course, I'm biased because that has been my line of research. I think there are a lot of great things that we can do by linking existing administrative data. To what degree this exercise is sustainable? So also, I mean, I think the important question is like, well, is this available to everybody? No, it's not. It's in my team, right? And so what is the problem? Like, can you make it available? Yes, but to make available and to curate the database, I will need the type of resources that currently I really don't have, and also the incentive. I mean, why? And these data, again, are available. And so a simple response to me, to everybody, say, well, just download it, and we will talk again in a year. Well, it's extremely complicated. And so also, this has been for us a great tool for training, for our both training people in biostatistics, both our PhD and postdoctoral fellow, because they are dealing with real data and with challenges they're going to face. So Harvard is doing something about this. So this is, I'm just going to do the plug from the administrative role they are playing. But it sounds great, right? I mean, Harvard helped build $168 million supercomputing facility. Well, so it's wonderful. This is a collaboration among different institutions. There are 4 institutions, Harvard, MIT, Northeastern, and Tufts, I guess. Now, this facility, the interesting thing about this facility is that the $168 million investment is for really the shell of a building and the access to the power. Now, any single, I think what is exciting though, that at Harvard, we are moving away from buying your own computer or your own server in your closet, but every type of hardware, piece of hardware that you want to buy will be part of the same group, which will be linked to power, which will be accessed to a much cheaper cost, so then we can consolidate computing resources. So I think that there is also, I think, especially in population health, which I think we are so much behind genomics. There is also this really fear of having your epidemiological data leaving your office. And so I think that there is we are very much behind in terms of try to understand that it's okay if your data are stored somewhere else. You don't need to have it your computer in your own office. So anyway, thank you for your attention.